So here we've got a 1.6 kilogram rock being released from rest. When you see the word drop, you can assume from rest. And it's released from a height of 15 meters from the ground. However, we don't want to know how fast it's going when it hits the ground. We want to know how fast it's going when it's only fallen maybe 5 meters. So by the time it falls 5 meters from where it started, it reaches a final height of 10 meters. 5 plus 10 is 15. So let's begin with our conservation of energy equation. Now at the beginning, the rock starts from rest, so my total energy before is just potential. And my energy at the 5 meter mark, well, it's definitely moving now. It's picked up some speed. So it's got kinetic energy at its final location, but it's also off the ground, so it also has potential. Now, one way to start all of these questions, we really only talk about potential energy and kinetic energy, and sometimes there's some losses, sometimes there's some heat energy produced. So if we write down the full equation, it can only ever look like this. The total energy before, at least for Physics 11 and possibly even Physics 12, consists of initial potential energy and initial kinetic energy. And all of that is always going to get converted into some final potential energy and some final kinetic energy. And if there's any heat produced means final, it'll appear on the right-hand side. Now, the only other term that might creep into there every now and again is if there's an additional force somehow acting on the object as it falls. The force would have to be consistent. So that would be an additional amount of work, as work is force times distance. This is very rarely introduced in Physics 11 and Physics 12, but that's our full conservation of energy, if you will. So all we do is itemize. So what do we have on the left? Well, it starts from rest, so definitely no kinetic energy. There are no external forces or pushes or thrusters on that rock, so there's no additional work done. It only has potential energy to start. When it's fallen 5 meters and it's 10 meters off the ground, it definitely has a final potential energy. It's definitely in motion. It has a final kinetic energy, but it didn't produce any heat because there's no air resistance, no losses. So our equation looks like my initial potential energy gets converted to final potential energy and final kinetic energy. So let's write down our formulas. mgh initial gets converted to mgh final plus 1/2 mv final squared. Now once again, if you've got an m in every single term, you can cancel it all off. So the mass, once again, does not matter. Now we're trying to find our final velocity. So let's get rid of this gh final by subtracting it from both sides. So I get gh initial minus gh final is equal to 1/2 v final squared. Now I can factor out a g if you like. You don't have to do this step, but there's a g in both terms, so I could write this as g h initial minus h final. I apologize. This should be an h final right here. And now I want to get rid of the 1/2, so I can multiply both sides by 2 and then take a square root. So I get 2g h initial minus h final. And if I take a square root, because my last step was to get rid of this square, I get root 2 gh initial minus h final is equal to v final. So plugging in the numbers, I get the square root of 9.8. H initial was 15. H final was 10. And when I do that, I get 9.9 meters per second. So when he's 10 meters off the ground, when that rock is 10 meters off the ground, it's moving at 9.9 meters per second.